welcome to this IFRR Global Robotics Colloquium on 10 years with Icup. And it's a great pleasure here to welcome our today's speaker, Giorgio Meta. And let me introduce Giorgio, but also introduce our guests in the front row today for this colloquium. Before that, and before handing over to Giorgio, let me say a few words about him. So Giorgio is a roboticist, a humanoid roboticist with passion for building robot systems and utilizing them to study embodied cognition. He is actually the leading developer of the iCub robot, and we will hear more from Giorgio today about the iCub. Currently, he is the scientific director of the Istituto Italiano di Tecnologia, IIT, and he is member of the founding board of directors of EU Robotics, and has been also professor for cognitive robotics at the University of Genoa and the University of Plymouth in the UK. Before that, he was also postdoctoral researcher at the MIT AI lab, and he received a PhD in electrical engineering from the University of Genoa. But let me say a few words about the story of iCub and the starting point of research on the iCub. And the starting point is a European project, the so-called RobotCub project from 2005 to 2010, which has the goal to build or to develop an open framework for research in embodied cognition. In particular, the objectives of this project were professionally documented, reproducible, open software and hardware platform, which is shaped like a child humanoid, the iCub robot, and understanding through implementations in the real world of exploratory and manipulation-based cognitive skills. By doing that, such platform would be the basis actually to study and to implement the initial period or the initial phase of human cognitive development in artificial technical systems. And one of the biggest goals of the project was also to build a scientific international community interested in research in robotics and in particular in embodied intelligence. The project finished, as I mentioned, in 2010, but the impact of the project goes beyond actually the duration of it. So the impact of the project is huge in the area of cognitive system research. As we know, the iCub robot has become a reference platform for many researchers actually, and for a large scientific community interested in pushing research in embodied cognition forwards. So I'm also happy that we have an exciting guests for our front row today. These are companions of Giorgio actually in his scientific career, but also iCub friends. So first of all, Professor Giulio Santini, whom you see also here, Professor Serena Evaldi from INRIA in France, Professor Angelo Cangilosi from the University of Manchester in the UK, Chiara Bartolozzi from IIT, the same also Daniele Bucci from the Italian Institute of Technology, and José Santos Vector from the University of Lisbon in Portugal. And with that, I will hand over to you, Giorgio, and we are very much looking forward to learn more about your experience and your journey with the iCub robot. Please, the floor is yours.
So thank you, Tamim. Just a moment to share my screen, and we are all set. So, I'd like to start with a picture of IIT because I think as we had in the past the opportunity to discuss, it was very instrumental to the success of the project. So the fact that we managed to have a lab where to, so to speak, nurture the design and the creation of iCub was actually quite fundamental. So, and this is also testified by the number of iCubs that we have at IIT and the number of researchers that are here in the front row actually working with the iCub. Let me go back in time a little bit to tell the story of the project. You had a chance to hear from Tamim a little bit, but I'll get to delve a bit deeper on how the project originated and what was the development of the project. So it all started when the European Commission launched a program on cognitive systems. This was very visionary, very bold in a sense, and also allowed the funding of large enough projects to attempt the design of a full human robot. Here you can see some of the institutes that were involved in the initial project and participated in the development of the iCub. It was truly a community building, and also the design of the robot was shared. Some of you probably have memories of that time. I have also memories of that time, and in particular, on one of the first meetings of the project. I think most of the people there in the front row were also there, or at least some of them. I think, Tamim, you should be there, but also there's me, although not recognizable because I was a different person. And but this was truly the meeting where we discussed the first architecture of the robot design. Starting from that meeting, we moved forward very quickly into designing the robot. It took about 3.5 years to actually start from scratch, design the full hardware of the robot, and think about the software architecture, and develop all that. So it was you know, a continuous effort, meeting very often to let's say fine-tune the design, and eventually leading to the creation of the iCub, the platform that since then we use for our research in embodied cognition. What we wanted to achieve is something like that. You forgive me for this reference to sci-fi, although this is one of the few positive reference of robots in movies, because this is a case where the robot was a very positive actor. So here there was no fighting, no you know, negative view of what robotics can do, but actually quite the opposite. There was a robot interacting with people, interacting very naturally, and manipulating the environment. These were, let's say, the keywords or the key elements we wanted to develop also on the iCub. Eventually, as I said, 3.5 years, we developed our, let's call, Formula One car. So the robot, the most complicated robot possible, and also a robot that I'm afraid to say it lasts the time of a Grand Prix, and then you have to actually fix it. So this was one of the challenges. We wanted a robot very complicated, but at the same time, any complicated engineering is not as robust as you may wish. But nonetheless, it allows us to do research. So bear in mind, the robot was designed for research and to develop research. It's not necessarily a robot that can do, you know, that can work for a long time without some fine tuning. Anyway, the key elements of the design, these were set at the very beginning of the project back in 2004. We wanted hands because one leading view on cognition is that we actually develop intelligence through manipulation. So we wanted a robot able or capable of manipulating objects to exert different type of grips. So we actually started from the hands. The hands of the robots are the most difficult component, and it took a while to make them small enough and flexible enough. And actually the entire mechanical design derived from the design of the hands. So for instance, in the hands, there's not enough space to put all the motors that can actually move the fingers. So this constrained the design to use tendon-driven actuation and place the motors in the forearms. So all these little elements of the design were actually determined by the way we did the hands. The other thing we wanted to do is have sensors, as many as possible, but be humanoid sensors. So we place cameras, we place microphones, the usual inertial sensors for balancing. But one important aspect is that we wanted tactile. Again, because if you're manipulating the environment, if you're interacting in the environment, you need touch. How did we develop touch? It's a long story, but eventually I think we managed to build a robotic skin that is one of the few examples of a skin that can actually be used to cover the entire body of the robot. Last but not least, the entire project is open source. If you go on the iCub repositories, you can download the entire software, the middleware that runs on the robot, and also the entire mechanical design and the electronics, all the drawings that theoretically are can be used for reproducing the iCub. Unfortunately, the iCub is made of more than 5,000 parts, and therefore no one built a copy of the iCub besides us because it was too complicated. Simply, it requires some professional skills. It's not something that you can do in a basement with simple machines. It requires milling machines. It requires the ability to build complicated electronics. So there's some experience needed in order to develop the iCub. But nonetheless, we managed somehow. Here, I'd like to show you what I was saying, the components, in particular, the tactile sensors that we developed for the iCub. And here there's a video showing one of the experiments where the robot is actually doing in-hand manipulation. So it shows the fact that you can actually use the tactile sensors in the fingertips to measure the forces, the interaction forces with the object, and move the fingers in a sophisticated enough way to do in-hand manipulation. The actual solution, very simple to describe, it's a capacitive sensing method, pretty much like the touch screens of the smartphones. So nothing different apart from the fact that we wanted something flexible, because of course it has to cover a robot that has a complicated shape. It's not just a flat panel that we needed to sensorize. Therefore, we made everything on flexible materials, and we ended up with a skin that can actually be used in experiments like this one, where the robot is being pushed around. It's in this case in a sort of zero gravity mode. It is using the skin to detect the point of contact. It's also using force torque sensors that are embedded in the structure of the robot to estimate the external forces and sort of zeroing the external forces in the control algorithm in order to follow the external simulation. So this is one of the examples that I think is very interesting. Unfortunately for the video, it's not very clear, but the robot is very sensitive. One finger is enough to move it around, and maybe you can perceive that, although perceiving forces through videos is a difficult task. Also, I mentioned the fact that we developed software. In fact, as part of the iCub, we developed a full-blown middleware, a bit like ROS for people that know ROS. Just that this was born before. There was no ROS at that time. So we had to write our own middleware in order to make sure people can program the iCub in a relatively simple way. The development started even before actually the iCub was born, but we decided to refactored the entire software when we started the iCub project, and since then we kept using the system for actually programming the iCub. The entire repository of the iCub software that I mentioned is open source. It's huge by now. There's all the history of development of the iCub. I cannot guarantee on the quality though, because I mean, you find here all the work by students, all our PhD work has been deposited in a sense in this repository, and but it's a very active community. There are about 400 commits every month, and there are typically about 300 people continuously posting something in the repository. And in terms of activity, if you look at some of the websites that collect statistics about the open source projects, we are top 2% worldwide, which is not bad. It doesn't mean, as I say, that there's good quality. It means, well, some parts are good quality, but it means that there's a lot of activity there. By the end of this year, or probably mid 2022, we will reach iCub number 50. This because since the project started, people started wondering whether they could buy an iCub. And we at IIT get ourselves into the task also of building copies of the robot for other laboratories worldwide. I must say that many of them are in Europe because the European Commission funding helped in paying for the cost of the iCub, which is kind of expensive. It costs about 250,000 euros. So it's not cheap, but as you know, you're buying a Ferrari Formula One car, so you expect to be pricey a bit. The other point that is interesting is that we try to build a community. And as you know, I like this idiom in English, building a community of researchers is a bit like herding cats. So cats are very difficult to herd. And indeed, coordinating this large number of people has been, or has proved to be very complicated. Very rewarding, I must say, but complicated nonetheless, because of course, every single researcher would like to develop things differently. Now we have, you know, more recently we got crazy people trying to attach jet engines to the iCub. So as you can imagine, maintaining coherent development in all these different directions has been an interesting exercise. We did it also through something that I'm missing so much because recently we weren't able to organize a summer school like in the past. This is an example where we actually based the full summer school on robot programming on the iCub. This happened for until 2019. Then we had to take a break, but we hope to be back very soon, of course. And this is a video that was prepared by one of the students back in 2013. I just wanted to show you a few images from them because
so this year was the 7th edition of the school, and very happy of the results. Especially I saw all students participating and being very late at night, which I think is commendable.
So I think you got the gist, at least of the project. This is my first break. I mean, if you like to open the discussion.
Yeah, okay. Thank you very much, Giorgio. Yeah, we will have actually several breaks during the presentation of Giorgio, and it's time for the front row guests to start asking their questions. But our guests joining us also have the possibility to post their questions to Slido. So the link is in the chat so that we can also discuss these questions with Giorgio later. So Please, the front row guests.
I got a question. I asked this question to PhD students during Vivas. Giorgio, it's not the time for you. You're a bit more senior than that, but I think the question will be appropriate. So what would you have done differently, knowing what we know, on the iCub, if we were to resubmit the proposal with few tweaks that would make it really, even better of of the success that clearly has achieved? Would it be hardware, scientific, software differences?
Yeah, thank you, Angelo. I wouldn't do anything different on the hardware and software side. I will give us more time to invest into research. I think the objectives that we set back in 2004 were very ambitious, but they require a life to develop them. I mean, it takes very long, and so either a larger project of the same duration, or a much longer project with the same partners, actually, that would have been very important.
Thank you.
Jose, just go ahead, yeah.
Can I go ahead? Okay.
Yes, please.
Okay. Well, Giorgio, it's very nice to revisit this journey and all these developments. Quite impressive to see all of this again. So you mentioned that the one major achievement, I totally agree, is this community building. So creating this massive community around this Formula One or Ferrari, as you say it, which I totally agree. So my comment or question there is, so besides putting a lot of people working together using this advanced setup, I think it was also very, very crucial that these people or these cats were really of different types. So the engineers, computer scientists, psychologists, neuroscience, maybe you could comment a little bit more on that. And the other thing that I was thinking to myself is that, so this is the kind of project that I think we should have one every 5 years or like a continuous development. If you see the people from physics that they do these accelerators, then they build the next one, but it never really ends. So maybe we should see ways to do a similar process. Okay, thanks.
Thank you, Jose. Yes, definitely the interdisciplinarity was key. I mean, you touched a very important point. I think it was inspirational on one hand, but also was the source of all the new ideas that we put into the project. So no doubt about that. Fostering interdisciplinarity is not easy, but in that moment, I think, as I said, the European Commission had a very visionary idea of projects where different competences could be mixed. So yeah. It changed since then, and that's why why we don't have another project every 5 years. I mean, I think the trend for a while went also into more applied, more show that robotics can have impact, which is all okay. I mean, but it's just a different type of research. So it wasn't so much on cognitive systems. I think we missed an opportunity there. I mean, could have been done differently, or it's a bit of a shame that we didn't have the opportunity to update the accelerator every now and then.
So Chiara, go ahead.
Hi, thanks, Giorgio, for this nice introduction. Going on about this topic of having interaction between different communities and disciplines, what I noticed is that most of the interactions have been on the software, on the development of the skills, on studying how the robot interacts with people. There was a bit less so about hardware. Integrating new materials, new technologies, so involving the hardware engineering community. So the question is, how do you think we could improve on this aspect, and which would be the communities that you would involve? Which are the most promising technologies you see for improving the platform?
Wow. In reality, at the very beginning of the project, we were there was a community designing the robot. It was more difficult later on because we also had to maintain and integrate all the pieces together. So that's the reason why the hardware mostly evolved at IIT. And also for what Jose mentioned, there was no a follow-up project capable of taking over the, let's say, the legacy of iCub in developing new hardware. With respect to what technologies to include, it's not an easy question. We've been trying for a while to involve people developing, for instance, new materials to be used for robotics. And it's a long process. And this may say something about interdisciplinarity as well. It's certainly there's room for improvement there. Would be nice if we managed to do that. I don't know whether it would require a project with a momentum comparable to that of RoboCub. So the first project that actually led to the design of the iCub. So that's certainly technology to be incorporated. Of course, then any other technology on the computational side, we tried a lot with different ways of doing computation, as you may know. We tried neuromorphic, we tried many different things. It's slow. Whenever we touch hardware, it takes a long time. So to be, not to give up though, but it takes some time.
I see the next question is coming from Serena.
Yes, thanks. So thanks, Giorgio. I think we all agree that this the history of iCub and iCub itself is like a success for robotics that is still unmatched, I think, worldwide. What is the thing that you would like to transmit, like the thing that you learned and you think like was the crucial element that you learned from this project, like through all these years? And then what is the skill that you see, the one skill or the more skills that you think are still lacking in this kind of robot?
So I think what I like to carry, I mean, clearly the hardware and the software will change, will pass. We may go and developing new things. So that's not the element that should be moved to the next project. What I think will be super nice is to maintain the community. I mean, with tackling project, let's say, our goals are so big and difficult that if we manage to reinvigorate the community, we'll certainly can embark into a new iCub project and go for the next stage for the next robot. So in this sense, this is let's say the take-home message is if we had the community pushing forward, we certainly now, 15 years after the initial design, we could do differently. Doesn't matter, but we could again start with the same momentum.
Okay. Daniele, just go ahead, please.
Yeah, thank you. Thank you, Giorgio, for the nice introduction. I mean, the iCub is definitely an incredible story, and anytime that we talk about this and we realize the incredible success of the robot. And but my question would be about your insights about the mistakes that the community did, if there are any, or if we can identify some of them. So, what is your, on the one hand, the first question would be, in your opinion, what did somehow did the community do wrong, if anything did wrong? So in your opinion, what are the lessons learned, and if you had to go back, you would do it differently? And this is the first question. The second question is, you mentioned Ferrari, no? And sometimes we see how the Formula One then translates the technology into products. So I wanted to know about your opinion about the technology transfer process that we can somehow derive from iCub, and how we could strengthen it.
So the mistake, I don't think there are mistakes that are so relevant overall, apart from perhaps from not managing to let's say, to make the robot even more a standard platform. For instance, I mentioned there was a moment where middleware for robotics was a new concept, and I think we missed the opportunity to really consolidate on that. At a certain point, we had certainly the largest group of users, and we didn't push that much forward for that. It was, I mean, whatever we developed was so much associated to the hardware that wasn't taken over by others. I think it's a small missed opportunity in that case, but you know, no time to complain about that. In terms of certainly the technology can be carried over into applications. Today, I'm not going to talk about that, but there are examples of industrial projects that actually derive from the development of the iCub. So I think today we stay on the research side, but of course it's a possibility. And I mean, whenever you do robotics, it's easy to see possible applications, not necessarily of the iCub hardware, but of what you do, what you learn with a complicated platform can certainly translate also into applications.
So we have actually one question from the audience regarding what can be done to keep the spirit of the iCub and the open platform development in robotics, but to make things more accessible to researchers. Do you have ideas how this can be done maybe in a more efficient way?
I don't know how to do it more efficiently. I think it works well enough with the existing sharing platforms that we have. The one thing that is needed is effort, and effort means eventually another project, so you need people to actually maintain and run the business, let's say. This requires another funded project, or a project that can actually put some money into that, because it's really a lot of work. I mean, researchers typically are focused on getting the results, especially students and postdocs. They would like to get the results, their research published, and then move on. So you require professional technicians and professional software developers, let's say, to keep things at the good level to share with others. And doing that requires certainly an infrastructure, also in terms of money or funding.
Mm-hmm. Okay, thank you very much. I think we continue now with the next part of the presentation.
Yeah. Okay, I wanted to enter a bit more into the details. Given for the sake of time, I think I have to go a bit faster now, but bear with me. So one of the, let's say, sources of inspiration of the iCub project was the work with neuroscientists, in particular neurophysiologists. We had the opportunity, together with Giulio, that is also sitting here in the front row, and Luciano Fadiga, neurophysiologist, to learn, in the first step, to learn about neurons from the motor cortex that are responsible for grasping, for manipulation. And the important aspect, or let's say that after discussing a lot, we had a very concrete message. Motoric information is very fundamental. also for perception. So whenever you perceive something, it's because you also have the possibility of manipulating the same object that you perceive it. So this was one of the famous results, the so-called mirror neurons, but not only. There are in the same area neurons that are, in a sense, activated whenever you see something, but in a sense, connecting what you see with the opportunities you have for manipulation of the object you're seeing. So inspired by this, we started reasoning that maybe this motoric information can be, let's say, factored in a recognition system. This is a very, very old experiment, but I wanted to use it as an introduction. Here in particular, we recorded a certain number of graph types of objects from a set of objects, and we tried to build a traditional object recognition system, but with a difference. Since we had motoric data, so we had the movement of the fingers while grasping the object, we tried to see whether this data can improve the object recognition system. Now, one possibility, of course, if you incorporate this data while you're grasping, that's easy because you have access to this motoric information. But if you're developing a purely visual system, you can still have a memory of the ways you grasp these objects. So what we done basically was to collect visual data, images as usual, synchronized with motoric data. So the movement of the hands and fingers while grasping the objects that we also recording. Now, if you remove the motoric data and you substitute with a prediction of what the motor act will be from visual data purely, this improves recognition nonetheless. In a sense, it structures the way you process your visual information and delivers better performance. So this was the data set. At that time, it was before all the deep learning stuff, so we didn't have, we could only process limited amount of data, and in fact, you see it's a limited set of objects. But this was, let's say, proof of principle that we then used later in more sophisticated ways. And this result that shows that basically, if you incorporate this reconstructed motoric data, and I'm in particular, I'm referring to the blue plot, blue dashed plot in this diagram, you see that you obtain better performance than a number of other possible recognition systems that you may develop. If you had the very blue plot at the bottom represents the case where you had perfect access to motoric information, which is not the case because when you're observing, you can only imagine what will be the action that you apply to grasp the object. So you cannot, you don't have access to the motoric information of the person you observe while grasping the object. Okay, to cut a long story short, this was sort of proving that there's something in motor information that can be capitalized when developing recognition systems. We also discussing as part of another European project, we got to learn that the area that is responsible for grasping is also responsible for speech in part. It's the so-called Broca's area in humans. So we, in particular, I'd like to refer to the experiment by Luciano Fadiga and colleagues that shows a very important or proves that this is the case. So they did an experiment, a transcranial magnetic stimulation experiment, where they presented two different types of phonemes to listeners while delivering TMS to the subjects. In particular, delivering TMS in two locations of the primary motor cortex that is related to the movement of the lips and the movement of the tongue. And the phonemes that you ask to recognize are actually phonemes that either require the movement of the lips, like B and P, or the movement of the tongue, like T and D. Okay, so having done that, what they discovered, that if you deliver a stimulation, let's say in the area of your motor cortex that is responsible for the movement of the lips, and you're listening simultaneously to a phoneme that requires the movement of the lips, your reaction time changes because of the stimulation. And this is the opposite if you stimulate the area that is responsible for movement of the tongue. So this means that there's a causal connection between the motor cortex and your perception of those phonemes. And this is a mapping that actually maps your muscles to your perception system. So this was inspirational. So what we decided to do is actually to incorporate, again, motoric information, like simulating, in a sense, your motor cortex in a system to perceive speech. This is the first implementation. Basically, we took, and here we were using deep neural network at that point. We took the speech data together with motoric data related to speech. So we measured actually the movement of the lips and the tongue, very complicated to do in practice, but very interesting. And we built a mapper that takes the sound and transforms into predicted motor information. And this, connected to a standard HMM-based speech recognition system, shows better performance. So in particular, if we start from, let's say, a state-of-the-art system and we look at the phonetic or phoneme recognition rate, this was done at the time we started the experiment, so it's not particularly new. We see that the incorporation of motor information improves performance by quite a considerable amount. So we go from 38% to down to 27%, which is being the phonetic level, the very first processing layer of any speech recognition system. This is an important result. Interestingly, we discovered also that the improvement in performance is highest when the phonemes to be recognized are difficult. Like, for instance, their consonants, the D, N, T, Z sound, that are the most difficult. So you don't improve much for vowels because they're easy to recognize, but you improve on consonants that are typically more difficult. So this is even better for the recognition system because you're solving a difficult problem. We complicated the architecture along the way. I'm not going to enter into the details. The reason is that in order to capitalize on small data sets, that is what we have, because there's no large data set that includes both motoric data and acoustic data, while there's tons of numbers on acoustic and on speech. We had to hack a bit on the architecture, on the complete architecture of the system. Anyway, again, to cut a long story short, when we compare this recognition system also with other systems, like a paper from Microsoft on some similar approach, or if we go for the standard Google Speech API, we see that we do better by considerable amount. And this was very interesting, also showing that this multidisciplinarity that we were discussing earlier is fundamentally important. We implemented something completely new because we had this interaction with neurophysiologists. Otherwise, who may think of going for motor information into a speech recognition system? Anyway, these are some of the videos that show the results.
I think this is the soap.
A video where from some time ago where there's the experimenter talking to the robot and asking the robot to recognize objects and point at the object.
Yes, you are.
Kind of very simple video, but it gives you the idea of what we eventually done with the system. We went also for something more complicated where we were using a synthetic analyzer to complement the basic phonetic recognition system. Okay, this let's say it's an addition. It's not necessarily so much the important aspect of the experiment, but it's interesting because it shows again that you can complicate things and go towards a proper speech interaction with the robot. So this is experiment number one. I'd like to move on to another line of research where we exploring the possibility of interacting with the robot and actually doing the opposite. So in the previous case, we had neuroscience informing us of, let's say, how to develop better methods for robotics. Here we have robotics helping neuroscience discover something new. In particular, what we are doing is studying problems related to human-human interaction using a robot as a proxy for the interaction. Advantage, the robot can be controlled, can repeat the same gesture many times very accurately, which is something that is very difficult to do if you're asking a person to repeat the same action. So you have complete control on the data acquisition, let's say, and you can still generate very sophisticated interaction patterns. Also, you can also compare the two. So you can compare the case where two people are interacting with the case where a person is interacting with the robot. And you can even check or ask the question whether the robot is more or less like a person. So you can try to distinguish the two cases where the person is interacting with another person or with a robot. Anyway, one experiment that we ran not long ago is so-called Posner Cueing, which is, or gaze cueing, which is basically the following. You have a sign that can be an arrow in the original Posner paradigm, and then you have a stimulus appearing, either congruent with the arrow, so the stimulus appears in the direction of the arrow, or incongruent, therefore appearing on the opposite side of the arrow. So we repeated the same experiment to substituting the arrow with a robot, and in particular with the iCub. So this is the video showing how the experiment goes. And you see the various possibilities. So there's a valid cue, or the robot looks a certain direction, but the stimulus appears on the other direction. There's a difference though. We manipulated one parameter. So the robot is either looking at the subject, or let's say not looking straight into the eyes of the subject. So it's either generating some prior interaction or not generating it. Now the result is the following, basically. We see that there's indeed an effect if the robot builds eye contact before moving gaze. And in the case of no eye contact, nothing happens. I mean, the valid or invalid reaction times are the same or not statistically different. This means that indeed, if a robot looks at you, there's something that happens and your reaction time again changes. Now, there are other parameters and things may change depending on when the robot looks at you. This may tell us something important when designing human-robot interaction interfaces, because the moment the robot looks at you changes the final result. So this is an experiment where the so-called SOA, which is this number, is basically the stimulus onset with respect to when you do the movement of the robot, changes in duration. So if you change this timing, the results are completely different. So again, this is an important message that when designing human-robot interaction experiments, there are tons of controls that have to be made in order to deliver one result or another result. We control these, let's say, numbers, or the same experiment was controlled also through EEG recording, showing that indeed we see a difference also in the EEG in some of the electrodes that are typically correlate with the attentional activity. And so we see here that that's indeed the case. And this was basically to prove even more that it's not just the reaction time, that is in fact a different processing mode depending on what the robot does, whether it looks at you or it doesn't look at you. So to summarize this experiment, joint attention in a robot or with a robot modulates the way you perceive the robot, and also that the robot itself is treated as, or the gaze of the robot is treated as a social signal, which is, I think, very important to know, and also delivers some more to neuroscience, because it helps understanding all the issues related to timing, to gaze yes or no. All these details can be singled out by using a robot as a stimulus. There's another experiment. I'll go very fast here because I think we're running out of time, and it's about let's say whether something changes in case in an experiment like the one I showed before, so an attention-based experiment, you create expectations about the action that is to happen. Here the robot is speaking and telling something about the object that is going to actually grasp and pass to the person. And the person in the meantime has to run or to detect a stimulus that appears on the table and decide whether the stimulus was a T or V, like in the previous case, whether it was left or right. So the fact that the robot is creating expectations on what it will actually grasp and pass to the subject changes performance. This is an experiment that was also mutuated for a more classical experiment in cognitive science, but the point or the result is the following. In case the action, so what the robot tells you is congruent with what the robot does, there's this effect, this Posner effect, let's say. So there's this change in reaction time. In case the situation is incongruent, nothing happens. And in the case neutral, where the robot doesn't say anything or doesn't say anything related to the particular experiment, you still see a difference. So, okay, so going back to the, let's say, take-home message from this other experiment, you know, it happens, or we can demonstrate that action expectation is actually important, again, when you're interacting with the robot, as much as important with human-to-human interaction. And also that the joint attention occurs at a higher degree when the gaze is incongruent. So we see this higher difference in that case. I think, again, this is a nice message in a sense, or a nice way to use the robot for a particular cognitive science experiment. So if you want, is the dual of what we saw earlier, where the cognitive science or neuroscience is telling us something. Here, we're using the robot for doing the opposite. We can have a break here, and then I'm almost done.
Can't hear you, Tamim.
No sound.
Oh, sorry. So yeah, thank you very much, Giorgio. Maybe you can stop sharing the slides now so that we better see the front row speakers. And let's have a break with a few questions from the front panel, but also the audience. You are more than welcome to post your questions to the Slido.
Maybe I can.
Jose, yes, please.
Okay. Well, it was very interesting again, this second part, and it's good to remind us that in this type of interdisciplinary venture, so sometimes the roboticists will get inspiration or learn from the neuroscience or psychology side, but then in some other cases, when everything is, let's say, close to perfect, we also suggest new hypotheses or experiments, or provide better insight to neuroscience, and so it's a two-way collaboration, which I think is very interesting. So what was crossing my mind was when the robot was designed, we were targeting at this period of development between 0 and 2 years, up to 2 years of age, which is a fantastic period in human development. I mean, sensory motor coordination, language. If we would go on developing this Formula One or Ferrari in the next project, would we still keep in the same, let's say, age period? Because there's so much we still need to know that is happening in this fantastic period. Or in your mind, we should also target other aspects that appear later on in time?
I will leave that decision to the researcher. But I think if I had to go back, I would still target that period, because I think it's very fundamental, is where you learn how we learn, in a sense, and therefore it's the most important aspect of what we like to. I mean, it's our let's say claim that a robot of that complexity, meaning the mind of the robot of that complexity, can only be developed through learning, and therefore, what better chance to observe the period where we learn the most.
Yeah, I was wondering if a robot could inform us as well about cognitive processes during adolescence, but that would probably be very challenging. Okay.
Very challenging.
So, yeah, Daniele.
Yeah, Giorgio, thank you also for this other part of the presentation. So while you were presenting this bio-inspired architecture, really it came to my mind the quote that nature gives architectures, nurture gives parameters, no? And but clearly then the physical properties of the Icup bodies are a little bit different from the physical properties of the human bodies. So the question would be, how much, in your opinion, how much was bio-inspiration as a constraint and that then limited the overall performance of the platform? And if you went back, somehow, would you push along putting bio-inspiration as in the cost function rather than as in the constraint for the development of the platform? So that would be somehow my question.
Yeah, but you know what? No matter how bio-inspired we were, it was only superficial bio-inspiration. And you're right. I mean, yeah, nature gives you the platform, but the platform that it gives you is extremely flexible, and no engineering today that can actually mimic that flexibility. So in a sense that we scratch the surface of the problem from the body point of view. And therefore, if I could push more for bio-inspiration in the body, certainly I will do it. But it's very, very difficult, because at the same time, we wanted something, let's say, with enough capability to be able to run actual experiments. Because conversely, if you went for, I mean, there are tons of examples of robot bodies that are even more bio-inspired, but typically it's very difficult to use them for sophisticated experiments. So I think with Icup, we tried to go for the trade-off of, okay, something that it works well enough with certain limitations, but at the same time is humanoid enough. And that's where we landed. I think it wasn't even a conscious choice. It was something that happened because during development of the robot hardware, we wanted to, I mean, we were always struggling with, okay, but we want to use it. I mean, the moment the robot is finished, I remember José, that was with his group responsible for designing the head of the robot. Immediately, we started doing eye movements, vision, with the first prototype, even if it wasn't finished, because we really needed a robot for developing research while still designing the robot. So there's no clear answer to your question, but it's certainly, you know, it's a challenge for the future.
But don't you think that really biology is the benchmark for us? I mean, we have somehow to find ways how to transfer all these performance of biological systems, in particular in the case of a humanoid, to technical systems. So what would be your idea or your thinking in this direction? I mean, of course, I think at the beginning, bio-inspiration, there are nice ideas which maybe don't scale up to a humanoid, but do we have another alternative?
No, not that much. I agree with you, Tamim. Especially for people designing humanoids that are. So if you go for humanoids, you have certain constraints. Then you can do it smaller, larger. I mean, this may be determined by the technology you choose to use. There can be other constraints. For instance, one constraint with the Icup was, let's go for electric motors, because we didn't want to deal with the complexity, for instance, of using hydraulic. We've seen incredible performance, at least from the motoric point of view, in robots that are hydraulically powered. Sure, it was a choice. A choice because we didn't want to deal with the other connected problems of running on hydraulic. But it's all, as I said, engineering as usual, it's a bit of a trade-off. You have always to take decisions, and then you get what is offered by technology. I agree with you that eventually you have to go into a technical system. So, and that's why we landed on certain decisions with the iCub. Once we understood that for us, also because of our backgrounds, perhaps, the electrical motors were the optimal choice, then we went in designing the hand of the robot, because it was the most complicated part where we wanted to have certain flexibility. And then pretty much everything else fell in place, because these were the major constraints in designing the robot, plus the humanoid one, which was, I think, to be considered.
Yeah. Okay, thank you very much. Yeah, maybe we continue with the last part.
Okay.
It's about the future now.
Well, no, I wanted to give credit now to some of the research that has been developed on the iCub that I didn't manage to present in details. In this case, I'll start from this video that actually is Angelo's responsibility, because this it's one of the first example of use of a deep neural network back in, I don't know, 2009 perhaps, when the hype about deep neural networks wasn't there yet. It came a few years after, but it was already an implementation on a GPU that we use for this experiment. Here, the robot was taught how to move an object and was replicating the trajectories and reenacting the trajectories to actually move the same object, lift it, and so forth. This is a piece of research by another member of the lab who's not here today, but it was part also of a project some of you were part of. Again, it's the grasping. So here the robot is looking at using vision to do a 3D reconstruction of the object and then planning how to grasp for it. This is again collaboration with people at MIT in developing methods for fast learning, fast and efficient learning, which eventually translates into being able to teach the robot, the iCub, how to recognize an object very quickly. And here in particular, what we've done, we use a deep neural network that we basically recycled in a sense. So we used it as a pre-filter, while the fast classifier was our own development. And in particular, what we've done, we work on a method that it's very efficient because on the way it performs optimization, avoids the more traditional, let's say, matrix inversion and goes for a gradient descent with something called a preconditioner, which is a way basically to tell the gradient descent method how to go straighter into a better direction. This makes everything faster and requires less data, which means that we can basically show an object to the iCub and the robot will immediately recognize or collect, let's say, a small number of images that those are enough for recognizing the object. This is another piece of, let's say, bio-inspired work where we develop let's say, prediction of contact on the robot. So a sort of a peripersonal space. And the robot is using vision to predict whether an object will get in touch with any body part and trying to avoid the contact. And this is, let's say, an extension of what you saw earlier, where the robot was in zero gravity and being touched and pushed around. Here, even before contact, the robot actually moves away. This is another piece of work that is very instrumental for certain things, in the sense that this is a controller that maintains or does balancing while doing force control, which is very useful for something that you may be wondering why we didn't show bipedal walking so far on the iCub. Here it is. And this is actually with one of the latest results where the robot is also doing step recovery. Fortunately, the video doesn't show so smoothly as it's supposed to be, but you get the gist again. So the robot is walking and also compensating for external disturbances. And the robot is still force controlled, which is very interesting and a good achievement, I must say, because it's not easy to, especially on a robot like the iCub. This is another video from the past in this case, but which I find it still very exciting because it shows some of the capabilities of the robot and in particular getting up from a supine position, which is not an easy task. I don't know if you tried yourself. I cannot do it. But, I mean, a robot doing that is it's very interesting. Also, because this the task itself is kind of a non-convex problem. You can solve it through reinforcement learning, but you cannot solve it through a traditional controller, because you have to basically accumulate energy before you have to go further away from the goal before you actually push and move towards the goal. So again, to show some of the possibilities. I wanted also to show that it's not always the case that everything goes well with the iCub. You have an example here of a robot falling. You can see the faces of the researchers there, scared by the accident. And this is actually very normal when you're trying to do complicated stuff with a robot. Last but not least, I just wanted to show you a couple of pictures of, actually there's a crazy one that I like, and it's the robot with the jet engines. This not yet flying, but we hope to see it flying very soon. And I hope to see it flying more than once, because of course, I mean, here is not a matter of falling, but if you fall after flying, I think it can get a bit, let's say, dangerous for the robot at least. And this is, of course, I mean, the dream of metaphorically going to the moon. And I think working on the iCub has been a bit like going to the moon. It was one of these projects where you dream of from when you're a little kid, and then you eventually build your own humanoid. Let me say thank you to all the front row panelists, because of course they're all contributors, very fundamental contributors of the iCub project. This is a photo we've taken at a group meeting sometime in the past, and interestingly, well, you see the size of the group. So you get an idea of how much effort is actually required for developing a project like the iCub. So I wanted to mention this because we had a little bit of discussion on what you need in terms of community building. I still think that this is key to achieve results of this type. And of course, I mean, I think we still in the condition where we have to herd all these cats together towards the ultimate goal of human robotics. Thank you.
Yeah, thank you very much, Giorgio, for the wonderful presentation. So yeah, we can stop the sharing of the slides so that we better see each other. And the audience, you are welcome to post your questions to the Slido. And now we have also time for continuation of the discussion. Serena.
Yeah, so I think this is super exciting. It's exciting to see there is also something that is a work in progress that is pretty crazy, which I really like. And so what is the direction that you would like to see next? Like a cheaper robot, bigger robot?
You know what? I think it will be time now to do two things. And I think we are well equipped to actually do it. One is maybe clean up of the design of the iCub in a sense, where by cleaning up, I mean, okay, we are 10, 15 years after we started the first design. There's new technology available. There are new ideas. We have experience. We have 15 years of experience actually with a robot. Why not going for a new design or evolving what we have in something better? Certainly, it won't damage our research because it will help carrying out more experiments, a more reliable robot, for instance, will help that. And the other aspect that we're also very well equipped to move forward with is, again, the rebuilding of the community. So again, try to go into a sharing of research that I think we kind of missed in the recent years. I think there are still opportunities for working on joint projects and moving forwards with the dream of making the robot a bit more intelligent. I don't know how intelligent it will get because, you know, this is I think with AI, what we see is typically that the goal is always moving a bit further from us. So we try to reach it. The moment we reach a certain goal, it becomes trivial, and then oh, there's a new goal, and the robot is not really intelligent. So this is something I would like to keep doing or keep seeing happening. Now, as scientific director, I'm not that much involved in research myself, but I like to keep observing what our researchers are doing and where they're going. So this will be interesting to see and to see what happens next, certainly.
Jose.
May I shoot now? Okay. Well, I just to mention again that I mean it has been an impressive amount of work, and the role that the robot has played to be a magnet for this community that you mentioned a lot, which and also this community of so not only cats, but I don't know, cats, dogs, birds. It's even more challenging than just herding cats. I think this is really very. Then for the future, I enjoyed what you pointed out. So I maybe also another challenge that is, so we know more about the surface of the moon than we know about the bottom of the ocean in this planet. So I would challenge also a diving iCub that could help us explore a big portion of our planet that still, I mean, is pretty much unknown. So I leave this challenge for you, for your thinking. Yeah, and that's it for now. Thanks.
Not to mention the depth of our brains.
Exactly. Also that, yes. or the final, the ultimate embodied Turing test that we could.
Yeah.
Yeah.
Absolutely, absolutely, definitely.
So what actually I liked a lot in the project and in this philosophy of research and development of the iCub is this bidirectional exchange between engineering and neuroscience, psychology, and we mentioned that earlier, that of course we take inspiration from biology and from neuroscience, but what's more important is that roboticists have to maybe ask the right questions and to guide neuroscience experiments. So if you have a wish, what kind of experiments would you like people to do in order to solve one of the challenges we have in humanoid robotics?
I can tell you the following, because this is something I was meditating, but I don't think I'll ever find the time to do it. So now we know something about the brain, and we have also in the last few years gained the opportunity of running simulations with large-scale neural networks. Not super large, doesn't matter, but I think I have a question there, which is trying to understand what meta parameters on these large neural networks determine performance. So now you basically, when you have to do, I don't know, image recognition, what you do, you more or less concoct a number of convolutional layers, a number of whatever linear layers, you do whatever. Everyone has a different recipe for that, and then you more or less figure out that it works. I will be tempted to try to understand whether the architecture of the brain, the fact that your visual cortex is always there and that there are certain layers made in certain ways, has anything to do with performance that you get. And this can be done on a robot, so that we can also model the motor cortex, not only the visual cortex, and can be done beautifully. With respect to the past, I mean, when we started with the iCub project, we had trivial amount of computation. Now, for instance, at the IT, we have a 4 petaflop machine. I think it's quite enough to try to do a bit better with respect to how we use bioinspiration to deliver a technical system. So this is just an idea. It's random, may not lead anywhere, but it's kind of something that is intriguing and may lead somewhere in understanding how the shape of a neural network actually determines the performance of the same neural network.
Okay. Just go ahead. Actually, if you have questions or comments, the front row, but also the audience, please post your comments to or questions to Slido. Daniele, please.
Yeah, I'm taking the occasion to ask questions to Giorgio. It doesn't happen so often that I have this chance, so I take the occasion. So, Giorgio, so we have this emergence of incredible, for instance, AI algorithms. So we have reinforcement learning, which is in hype again. So where they can do very incredible things beyond human things in certain contexts. Then we have also robots that somehow do the backflips. Okay, so they show some very good performances from the physical point of view. So one may wonder, well, okay, so we have somehow tools and methods nowadays, as you were mentioning, that could enable cognitive intelligence. And then we also have somehow technology and in order to enable robots for motor and effective intelligence. So, but however, for the time being, these two communities seems to not understand how to put the pieces together. So I wanted to know your insight about this. So how should we put the blocks together now?
Well, we have to do it. I don't have any specific insight. I agree with you. There's a lot of model-based stuff on one hand, and maybe the backflip is actually obtained by tweaking and the accurate engineering, very beautifully done, by the way. And on the other hand, there's people that are purely data-driven, let's say, and so they don't care about anything else. Maybe there's something in between to be discovered, where we try to factor in constraints that are, in my case, if I have to bet on something, I will bet on some biological, whatever, inspiration. Also because of what a solution to a technical problem can tell us about our let's say, the functioning of our brain, which is very, very interesting. So maybe as I was mentioning earlier, the architecture is actually something that determines the performance. Maybe there's an architecture that is ideal to store certain models. I'm thinking of the dynamic model of the robot. Maybe you have a specific way of constructing neural networks for storing that piece of information. So there may be constraints like those that can be mixed with a completely model-driven or a completely data-driven approach. So why not? I mean, it's sort of a way to reconcile the two way of thinking.
Yeah, so we have a question actually here in the chat. Very nice question. Are there any plans to explore cooperative tasks between multiple Icups?
Yes, we did it actually, and I mean, I'm not the one doing it, but there's Daniele, who's here, is actually trying that. Also because the control algorithm, once you develop a controller for actually interacting with the person, you can translate entirely that controller to make cooperative robots. So we tried a few things in that direction, and we're doing something. So it works.
Yeah.
It's a bit more expensive than a single iCub though, because you need to.
Yeah, as you know, physical interaction with the real world is really very important for the emergence of cognitive abilities. So so far from what you showed or what you did, this is still limited to grasping or maybe disturbances during walking. And one of the initial hypotheses of the project was really this manipulation guided emergence of cognitive abilities. So do you think this is still valid, or is there any ideas or people also working in this direction? On the
I don't know whether, there's still people working, but I don't know whether the same idea, I mean, the idea is still valid and very valid. I think it's one of those things that I regret not having explored more deeply at the time. But of course, I mean, you cannot do everything. But I think it's still a valid research path. So going from manipulation to cognition, studying how you can learn from manipulating objects, how you can learn affordances of objects and so forth. I mean, I think this is still, I don't know, maybe you guys know more of research that is happening right now on that topic, but I think it's still a great opportunity. I like to see happening, or maybe it's happening, as I said, I'm not aware of that.
Okay.
Maybe I can pick on that.
Yeah, sure.
Yeah.
Well, I think a number of those research questions, like the one Tamin mentioned and Giorgio referred to, they are still ongoing in many groups. So we are also continuing a bit in those lines. What I sometimes ask myself is if I could change some fundamental characteristic of the robot that would help in my research, for example, addressing the issue that Tamin just raised, what would it be? And what comes to my mind very often for physical contact and manipulation would be a little bit more of soft materials and compliance with, which helps a lot when you touch the physical world. So I wonder if there are any plans or thoughts along this direction, or if other people also share this wish list, so to speak.
Actually, having a soft iCub would be less dangerous for the flying. So if the flying iCub,
especially for
another
landing,
landing. Yes. It will that for the landing, I would say.
So it's a soft iCub in the plan, or not really?
Well, it will be a very beautiful project, I think. It's very challenging. It's very challenging. I mean, it's always so exciting when we go seeing robots worldwide to see these soft robots, these very articulated, very human-like robots. I mean, it's so beautiful. But then the next question is whether you manage to use those robots for tasks like walking, like manipulation. So it gets very, very tough. But I mean, we really, for that, we will need to create a group of roboticists, yes, but also mechanical designer, more on the knowing the materials, and also material scientists, maybe inventing new ways of doing certain things. It's probably one of those. This is going to Mars, not to the moon.
Or perhaps hard bodies but soft hands, maybe could be a sort of a...
Could be a starting point, yes.
Hybrid,
Absolutely.
Good.
Okay. So, I mean, you know, this success of the iCub, of course, everything started with this RobotCub project, which is actually, let's say, compared to investments in research in these areas, is rather a small project. Of course, a lot of other additional projects contributed also to the current success. But IIT has been pushing this field of research a lot, actually, right, in the past. And now in your role as scientific director of IIT, so you could also contribute actually to the research by providing more resources, of course, for this type of research. In particular, building the next generation of cognitive humanoids, but also the continuation of this community building efforts. Are there any plans or?
Yes. Actually, Giulio is here. He's the main person behind the idea of the community building, specifically for cognitive robotics. So there's a plan. For now, we're trying to, let's say, collect the interest around the focal point. We call it initiatives on a number of topics at IIT. One of the initiatives is actually around cognitive robotics, focused on the iCub. So this is, let's say, a starting point. If we manage clearly to bring resources on this specific topic, this can be reinvigorating the iCub per se, but in general, the field. It's been a bit of a shame, I think, that, and it's not I mean, I know the reasons, but the European Commission started with this beautiful program during the framework program 6, which was the cognitive systems program. And this one continued a bit in FP7, then Horizon kind of faltered until the point they realized AI was blossoming again. And I think we had this crucial, let's call it a crucial development period, where we missed seriously an opportunity because the community was kind of disoriented for a moment to say, okay, we invested a number of years on cognitive systems, then there was a gap, and now, you know, AI is coming back. So this was I think for a moment we missed momentum. Now it's gaining momentum again, but of course we have to catch up. But the possibility is there. I mean, given the now coming Horizon Europe, there's certainly a possibility to develop and build on that.
Yeah.
I see many existing calls, opportunities, and so forth.
Yeah, so we are running a little bit out of time, but
no problem.
Oh, sorry, Giulio. No.
I mean, I didn't want to steal the stage to Giorgio, so I didn't make any questions. But I mean, this idea of you know, this last point that you make about what is the next step in terms of community building, I think it pulls a little bit too much to stay behind the scene. So I think, you know, as to the initial goal, when I wrote the initial proposal, I mean, there were these three pillars: the platform, the community, and cognition. Okay, the platform and the community has gone well, I would say better than expected, you know, because 50 robots was a dream at that time, you know. On the other hand, the third pillar, the cognition part, has produced a lot of very interesting research results and has produced a lot of nice collaboration with neuroscientists. But still, we don't have, now we call it an architecture, but it may even be less than an entire architecture. We still miss the sharing of that aspect of the platform, which was the main reason why the iCub was built. So in that sense, it has been less than expected. And I think it's now time to do it, because people have the interest very much on these aspects. The platform is more or less stable, and the community is there, you know. So that so I would not push very much toward improving the platform, even if it can improve, of course. But sometimes, you know, improving the platform divert the energies toward problems which are important but not essential. While now I think we need to address other things. I think
don't say the platforms are not essential. Actually,
no. The platform are fundamental. I mean, this is embodiment, so the platform are fundamental. But what I'm saying is that if you continue improving the platform without improving cognition, you will end up doing a somersault until the end of the time, and that's going to impress people, but it's not going to go where we would like to go. You know, having more intelligent robot, but also understanding better the intelligence. I mean, embodiment is fundamental. That's the way we are doing.
Fully agree. Okay, we are running out of time, but there is a last question from the audience I would like to take to Giorgio. Have you ever conducted experiments that a human and an iCub live together to do long-term tasks?
No, we never did that. I know there are people doing research where they're trying to have a robot, you know, go for long term, but I don't know how successful they are, because I'm pretty sure at the moment the robot becomes boring after a short while. I mean, the interaction is limited. So the experiments for us are typically the laboratory experiments. Sometimes we move the robot somewhere else. We can simulate being at the specific location, but the experiments are always within, you know, the range of a typical research experiment.
Thank you. Okay, with that, let me conclude this wonderful IFRR colloquium, 10 years iCub. Why actually 10 years? It's more than 10 years, Giorgio, right?
Yes.
But we can discuss that during a beer, maybe. I would like to conclude. Thank you very much, Giorgio, for all your contributions to the field of humanoid robotics and cognitive humanoid robotics. And good luck in your new mission as scientific director of IIT. I would also like to thank our guests in the front row for the nice discussions, but also all the audience who joined us today. And very important, maybe a continuation of the last discussion we had regarding manipulation and how far has been done in robotics in terms of manipulation. I would like to point out the next IFRR colloquium, which will be on May 13th on robotic manipulation, and it will be moderated by Professor Oliver Brock. So with that, thanks a lot to everybody and have a nice good night, nice evening, and good afternoon. Yeah, thank you. Bye-bye.
Bye.
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 Bye.